Hey guys, here I'm going to talk about just some visualization of the functions that I covered in the previous video where we created our generic list class. And I mean, some of the methods that I created are a little bit tough to kind of realize what they're actually doing. It just takes some time, and I think it'd be easier for you guys to see a visualization of what's going on with an example. So let's proceed. So the first method that I want to talk about is recursion copy. So up above this first code block that you see here is the source code for it, right? It takes a pointer to an S list called node, and if node is not equal to the null pointer, we call recursive copy again, right? So this is a function that's recursively called, so it keeps calling itself over and over, and eventually when it can't call itself anymore, it's gonna call the add front method of our linked list class, and it's going to add whatever values in a node to the front of our generic list. Then we have three dots to represent some code later, and what's highlighted here is an example of a method call for this method. In the test code that I had, I think I had Reccopy lst.front. So lst is a generic list class. So it gets the front of that list, and that's what we use for recursion copy. And for this example, more specifically, I'm going to say LST is going to be a generic linked list that has 4 items. They're integers. Simply, it's a sequence of 1, 2, and 3. The first node has a value of 1, the second node has a value of 2, the third node has a value of 3, and the fourth node has a value of 4. First, let's discuss the first Reccopy method call. So when we call it here where it's highlighted, this is the first recursion copy method call. So node is going to be at the front of the list, and I have that there. So we have node pointing to 1. So first we check if node is not equal to the null pointer, which is not, because it's pointing to a link to an S list, right? It's pointing to an element of the linked list. So then what I'm going to do is that I'm going to call recursion copy for node next. Well, what's node next? The second node here, which is going to be pointing to the second element of our linked list, which has the value of 2. And something that I want to highlight here is that this is the second time that we're calling Reccopy. So within Reccopy, we're going to call it one more time, which is this same function call. And then we do the same check. We check if node is not equal to null pointer, which is true. So then we call recursion copy again for node next, which is going to be the third element of our generic linked list. So now we're in our third recursion copy method call, and we keep checking, right? If node is not equal to the null pointer, we're going to call recursion copy again. And if it's still not null, we keep calling it until finally, in our fifth recursion copy call, our node is equal to null. So we don't execute this if statement on the fifth recursion call. So since this is a recursion function call, the first calls the second, and the second calls the third calls the fourth, and the fourth calls the fifth. When the fifth method call is done here, we're going to go back up to the fourth, which is going to be this. And when we have Reccopy here, recursion copy here, that was going from the fourth call to the fifth call. But since the fifth method call is over, well, we go one level up to the fourth method call. And what's left to do is to do add front. So we add front to the node value that's there, right? So node is pointing to 4, so we take the value 4 and we add it to the front of our linked list, our current linked list that calls Reccopy, which I just call self. Then the fourth method call for recursion copy is over. So since the fourth call is over, we go one level up to the third call. Here node is pointing to 3, so we take 3 and we add it to the front of our list, and then we go to our second function call, add the second node to our list, and then we go to the first method call where this was the original method call. And finally, its data, which is 1, gets added to the front of the linked list. I hope you've noticed something, and that we've copied our linked list. So we start from the back and we add it forward, and as we keep going one level up, right, we're copying that data over. So with this, we've successfully copied the data from LST over to ourself, the linked list class that calls this method, while preserving the order of data. And this isn't exactly easy, to come up with. So, I mean, I hope as you see this, you kind of get an idea of what it's done with this visualization. And hopefully, if you find yourself in a position where you can use this method, I highly encourage you to do it. It's really neat. And this is our visualization for recursion copy. So now why don't we move on to our next method, which is called add front. So when it comes to add front, we need to take two cases. The first case, which is I'm highlighting here, that we have an empty linked list, right? That front is equal to the null pointer. We have our input x data. We've allocated a new structure called new node, and we set new node's value equal to data. And that's represented by the box here that contains data inside of it. And below our little box is the state of our generic list. And it's empty because both the front and the back are pointed to null. So when that's the case, what we need to do is that we have node.next pointed to null. Then we have back equal to new node. And once we're finished with that if part, we go to the bottom, right, where the next highlighted bit of code is, and we set front equal to the new node and increase the size by 1. We go from a front and a back pointer that's just pointing to null, and we assign the front and the back to point to the data because we have an empty linked list. And then when we have a new value, well, that's the only value. So if there's only one value in our linked list, well, the front and the back are the same thing. So that's the logic here. The next case is when we don't have an empty linked list, and it can be one value, it can be 10 values, 100 values, whatever. So I have this linked list below data that's just a ... to z. And I mean, what I want to show here is that this can be just a and z by themselves, or we can have like the whole alphabet in between a and z. That doesn't matter in this code because here what we're going to be doing is that we're going to be adding data to the front of this entire list. But this is that second scenario that I'm thinking of when it's not empty. So what I do is that I say new node next is equal to front. So here I'm attaching this node to the linked list. And since it's attached the way that it is, right, since new node next is equal to the front, well, it becomes our new front. So I need to reflect that, and it's done with the highlighted code here. And of course I need to increment the size by 1. Next comes add back, and this isn't too bad. We start by assuming that we have a non-empty linked list. And again, similar to add front, we have some arbitrary linked list, a to z, ... That node can be nothing, or it can contain, letters b through y. That idea doesn't matter. The idea is that there's more than one value here. There's more than one node in our linked list, and it's not empty. So what I end up doing is that when I say back next is equal to new node, is that I'm establishing that link from the end of the linked list to our new node. But with this action, well, data is now our back, not z. So I need to reflect that. I need to have back pointing to data, our new node, our new back. The other case is when we have an empty linked list and we need to have data become our only element. So first I have front equal to new node, and then I have back equal to new node. So we go from an empty list similar to add front when it's empty to a linked list that only has one element on there, right? And of course, if you think of other scenarios where you can add a linked list, make sure to include it in your code. Maybe I'm missing something here, or I have something wrong. You yourself, if you go about creating your own class like this is the things that you have to consider. And this is tough, right? You can't always predict, all future scenarios of your class, but as you program and gain more experience, you can kind of get a better idea on predicting possible errors. And something that I want to say is that here I say if front equals null pointer, but you yourself can use the empty method if you want. And that's the same all the way for add front, right? Here I say if front is equal to null pointer, I consider empty, but I can call the empty method itself too. It's just a different way of doing the same thing. So now let's move on to remove front, and this is gets a little bit trickier just because adding data is relatively easier than removing data. So for a linked list, I should say. So here we have our node to delete, and we have it pointed to the front because we're going to remove the front. So then we have front is going to be our new front, which is front.next. So when I have front equals front next, this is what's going on. I have it go from front pointing to A to now pointing to B. And then I need to do some checks. If front's not equal to null, which is correct, but front next is not equal to null pointer. So I skip that. So then I delete the node to delete, and I'm left with this new linked list where I removed the front, and whatever was second in the linked list, which is B, has become the new front. Next, I go to the case where we go through front equals front next, and our node to delete is going to be A. But here we have if our front is equal, or front next is equal to null pointer, then we're going to set our back to null pointer. And actually, as I do this, I realize that this isn't exactly correct. What I should check is that if front is equal to null pointer, then I should set back equal to null pointer. But anyways, the deletion is the same, and we have our node to delete, and we do remove front. The problem is here is that under this circumstance, back is equal to null pointer when it shouldn't be. So what I'd actually like to propose is having this method as your remove front. When if your front is equal to null pointer, after you've shifted front to front next, then back is equal to null pointer. With that, we're going to go to our last method, remove back. And this is a little bit more complicated just because this is a singular linked list that can only go forward. So our front of our linked list is the only one that has a connection forward. If we look at our back, well, our back can't go backwards because there's no pointer pointing to the back, right? So that can kind of raise a problem. So here I have just my generic linked list. I have A to Z. I have at least 2 elements. I mean, here I put 3, you know, and we can imagine more, but here I have at least 2 elements. So first I set the back, and that's going to be the node that I'm going to delete. And I'm going to say if front.next is not null pointer, meaning that there's more than one node in our list. Well, if there's more than one node to our list, then I need to go to the second to last node. So what I do is that I create something called new back, and it's equal to our front. And it could be the case that our front, if there's only 2 elements, our front can be the second to last. Right, so if that's the case, then I skip the while loop. In the case that it's not, that there's more than 2, or you know there's 20, I need to find a way of getting to the 19th linked list. So I have this while loop where I keep iterating and I keep iterating until the next value is going to be our back. If I say while new back next is not equal to back, this means that I'm going to go until the second to last element, one before back. And once I found my new back next is going to be equal to null because it will, in this case, y is going to be our new back. And I set back equal to new back, thus essentially removing removing all links to Z. And once that's done, it's safe to delete it. I can call the delete keyword and delete that node. And I've removed the back, while having my back pointer pointing to what was the second to last element in our linked list. Finally, we have the case where A is just by itself, and if it's just by itself, well, we need to remove it and have everything pointing to null, right? Because the if statement above, because right now I'm talking about the else, but above in the if statement, that only applies if there's more than one. So we need a case if there is only one. So then we have that. We have front and back equal to null pointer, meaning that's going to be empty. And then we delete our node. And well, that's actually it. I hope this visualization helps, and I'll see you in the next video.